Good morning, everyone, or good afternoon, depending on where you are. My name is Marissa Waterman. I'm the Marketing Director here at AAEES. We're so happy to be doing this webinar today with the LA County Sanitation Districts. After our presentation, we'll open up the text panel for questions. You'll be able to type your question in the left-hand side of your screen where it says Attendee Chat. The three speakers will answer as many of those questions as possible, and we'll also have the speakers' contact information available after the presentation, so you can email them with questions as well. I'm going to go ahead and introduce the speakers, and then we'll get started. First up, we have Carl Glass. Carl is a mechanical engineer in the Reuse and Compliance section with the LA County Sanitation District. For the past 34 years, he's been working on programs that apply technical engineering principles to resource recovery operations. He received a Bachelor's of Science in Mechanical Engineering from the University of Delaware and a Master's in Environmental Engineering from Loyola Marymount University. Carl will discuss operational challenges and innovations at TLC. Our second speaker today is Brian Polson. Brian is an environmental engineer in the Air Quality Engineering section with the LA County Sanitation District. For the past 5 years, he's been evaluating regulations and audits to ensure compliance. He received a Bachelor's in Chemical Engineering from the University of California, Irvine, and a Master's in Environmental Engineering from California State University, Fullerton. Brian will discuss air quality challenges and findings at TLC. Our last speaker today is Larry Wong. Larry is a civil engineer in the Wastewater Research section with the LA County Sanitation District. For the past 12 years, he's been working on research programs that help develop practical solutions for the public sector. He has a Bachelor's in Civil Engineering from the University of California, Berkeley, and a Master's in Civil Engineering from the University of California, Los Angeles. Larry will discuss research challenges and strategies at TLC. So first up, we have Carl, and Carl, whenever you're ready, go ahead.
Thank you, Marissa. Welcome, everyone. Thank you for joining us today, and thank you to the American Academy of Environmental Engineers and Scientists for hosting this webinar. I'm going to start off by giving you a brief introduction to the Los Angeles County Sanitation Districts. The sanitation districts are 24 independent special districts serving about 5.6 million people, covering approximately 850 square miles, made up of 78 cities and unincorporated areas of Los Angeles County. The sanitation districts construct, operate, and maintain wastewater treatment facilities, operate and maintain collection systems, and are responsible for disposal and transfer of collected solid waste. An integral part of our mission is to convert wastes into resources. To this end, we recover recyclable materials, including recycled water, and produce green energy. Now for the star of the show, let me introduce you to Tulare Lake Compost, or TLC, the sanitation district's only fully owned and operated biosolids management solution. TLC is located in the Central Valley of California, about 200 miles northwest of Los Angeles. It took over 10 years to permit, design, and construct. The facility is designed to be constructed in phases, utilizing state-of-the-art technology. Permitted at full capacity for 500,000 wet tons per year of biosolids, it is currently built to a capacity of 100,000 wet tons per year. And it has been in operation since January of 2016. In this presentation, we will discuss the unique opportunity and vision at TLC, as well as the challenges and research efforts that have brought the facility to where it is today, and how we developed a system that meets our throughput goals and compliance with environmental regulations. As I'm sure most of you are aware, one of the byproducts of wastewater management is biosolids, which happens to be the most difficult to deal with. 4 of the sanitation district's wastewater facilities produce biosolids: the Joint Water Pollution Control Plant, or Joint Plant, and the Valencia, Lancaster, and Palmdale water reclamation plants, in total producing approximately 488,000 wet tons per year of biosolids. This represents over 1,300 tons per day, over 50 trucks per day, every day, and this material has to go somewhere. In the 1990s, the The sanitation district's biosolids management consisted of composting and landfilling. 20% of the joint plant's production was composted on site. The remaining 80% was landfilled. That landfill was the Puente Hills landfill, also owned and operated by the sanitation districts. Unfortunately, odors from on-site composting eventually led the districts to cease these operations. In the early 2000s, biosolids management options started to dwindle. Due to the closure of the Puente Hills landfill, the end of the on-site composting operations at the joint plant, and land application bans throughout the state. The districts needed a solution. The solution had to be reliable. While the districts continues to utilize a number of third-party biosolids management options, to increase reliability, we wanted an option that was fully owned and operated by the districts, and was sized to handle the district's full biosolids production. And it had to be environmentally responsible to turn this waste into a valuable resource. When considering locations for composting, California's Central Valley seemed to be a very good fit. There was lots of available land. It's one of the largest agricultural regions in the country. There was an abundance of wood waste and a huge demand for fertilizers and soil amendments. Bear with me. There we go. In 2001, the districts entered into an agreement to purchase 14,500 acres from Kings County landowner Westlake Farms Incorporated. A small portion of the property was set aside to develop a state-of-the-art composting facility. Compost produced by this facility would be used on the remaining agricultural land by the former owner, now tenant, through a lease agreement. The remaining adjacent land is sufficient to handle all compost produced by the facility at full permitted capacity. So here's the vision for TLC. Take the highly treated biosolids from the joint plant, blend with the abundant local agricultural wastes, and produce EPA Class A EQ compost to be applied directly to the land owned by the districts. So what is this Class A EQ compost? Biosolids coming off the wastewater treatment process are stabilized and reduced in volume through digestion, then dried to about 29% solids. These biosolids are mixed with green waste or agricultural wood waste containing the necessary carbon and water. Under aerobic conditions, microorganisms break down this organic matter and give off heat. Heat action over time destroys pathogens, producing compost. More wastewater agencies are turning to composting as a means of biosolids management. It's environmentally friendly since it improves soil health, increases crop yield, reduces irrigation needs by reducing evaporation, and reduces dependency on chemical fertilizers. In addition, it mitigates climate change due to carbon sequestration by actually putting carbon back into the earth. It also contributes to the state of California's goal of organics diversion from landfills. The EPA defines Class A EQ compost as follows. Biosolids that have been treated beyond what normally occurs at the treatment plant level, including the following two numeric criteria. The biosolids must have been treated by a process to further reduce pathogens, or PFRP. Purpose of this criteria is to ensure that pathogens such as bacteria and virus are killed off to make the material safe to handle. To meet the PFRP criteria, the compost has to be kept at a temperature of at least 131 degrees Fahrenheit for at least 3 days to ensure the heat kills off the pathogens. The biosolids also have to be treated by a process to ensure vector attraction reduction, or VAR. The purpose of this process is to reduce the attraction to the compost by animals or insects that can carry disease, such as rats, flies, and mosquitoes. To meet the VAR criteria, the compost has to be maintained at a temperature of at least 104 degrees Fahrenheit for at least 14 days. While we encountered a number of challenges in bringing TLC online, the biggest has been related to air emissions. So at this time, Brian Polson is going to give us some insight to the air quality challenges at TLC.
Thank you, Carl. So I'll start off by providing a short background on air quality and why it's a challenge to TLC. This map shows the areas with the worst air pollution in the country. The two areas which are classified as extreme non-attainment zones for ozone are colored in red and are both located in California. And TLC is right in the middle of one of them. What this means is that the local air district has to closely regulate emissions, which results in hundreds of regulations that we have to follow. And this relates to composting because composting generates emissions. This is a picture of an uncovered and active composting pile, and you can see the steam coming off the top, which brings along pollutants with it. The two main emission compounds that we'll be talking about in this presentation are volatile organic compounds, otherwise known as VOCs, and ammonia emissions, which are both generated from the composting process. Now, because the facility is in a non-attainment zone, the local air district, which is the San Joaquin Valley Air Pollution Control District, has to establish a limit on how much emissions we can generate per year. And this ultimately determines the amount of biosolids that facility can process. And before I go into how we are maintaining compliance, we need to take a look at the composting process. Now, composting is an aerobic activity. At TLC, we operate positively aerated static piles. Once the biosolids are mixed with agricultural waste, the material is placed on top of underground aeration headers, which are connected to blowers. And these blowers draw in ambient air and push it through the compost pile to provide the compost with oxygen. Now, emissions from within the pile would be pushed out through the surface. So we need a method on how to capture and reduce these emissions before they reach the atmosphere. The way we achieve this is using the synthetic fabric cover system, which is the technology that's used at TLC today. These covers are made of the same material as the thermal jackets that you can find at outdoor equipment stores, and they work in the same fashion. This system uses the fabric covers which are laid over the windrow compost pile being constructed. The fabric is breathable and provides moisture retention, but it prevents outside water from coming in. It also acts as a thermal insulator to maintain heat within the pile to keep the material composting. Now, these covers actually control emissions. This diagram shows a cross-section of a covered windrow pile and what's happening underneath. As the steam from the compost mix rises up and hits the cover, it condenses and forms a moist biofilm layer on the underside. And this is the main control device. So as VOC and ammonia try to escape through the cover, the biofilm layer captures them and returns them back into the compost pile to be further degraded. And these are some of the pictures of the fabric covered piles on site at TLC. You can see some of the more specialized equipment for the system, such as the tarp winder in the top right, which is used to place and remove the covers. The system is also a three-phase composting process, which calls for turning up the piles in between phases. This involves removing the covers, moving their material around to fluff it up, and covering the pile back up again. Now, during the facility design, we wanted to ensure that the fabric covered technology would actually perform in controlling emissions. So back in 2007, we conducted a pilot study at the Cedar Grove composting facility located in Seattle, Washington, which was already using the fabric covers. We trucked over biosolids from the joint plant and agricultural waste from the Central Valley to construct test piles. And we sampled the emissions coming off at the top of the cover surfaces. We did tests for both VOCs and ammonia emissions, but I'll mainly focus on VOCs for this portion, since these are the emissions that are the limiting factor for throughput. From the pilot study, we obtained a VOC emission factor of 0.2 pounds per ton of compost mix. And with our facility's emissions cap, this provided us a biosolids throughput of 500,000 tons per year. This throughput level is important because it allows us to process all the biosolids produced by our wastewater plants that Carl mentioned beforehand. Now we move into 2016, which is when the facility began operation. And as part of our permit requirements, we needed to conduct a compliance test to determine what emission factor we would achieve at TLC. And that number came out to 2.6 pounds per ton, which significantly lowered our throughput to 39,000 tons per year. This caught us by surprise as the number is more than 10 times higher than what we observed in the pilot study. To verify if these results would be consistent, we had another test performed as soon as we could in February of 2017. And during this compliance test, we achieved a lower VOC emission factor of 0.75 pounds per ton with a throughput of 135,000 tons per year. But this is still a far cry from what we've seen before in the pilot work. So what caused the difference between the results we saw at Cedar Grove and what we were achieving at TLC? Another look at how the fabric covers control emissions. The covers rely on that moist biofilm layer developing underneath the cover. However, the Central Valley experiences high temperatures during the summertime, where it will frequently reach above 110 degrees Fahrenheit. And when this happens, the surface of the covers can easily hit 140 degrees. What we've seen is that when the moisture inside hits the covers, it'll flash right through and it won't condense. This means that the control layer doesn't form, and some of the emissions are allowed to pass through the cover. This helps explain why the Cedar Grove pilot study had much lower emissions, since it was done in the dead of winter where they had trouble even getting solids out of the truck because they were frozen to the walls. And with those cold conditions, the moisture had no trouble condensing on the cover and forming that control layer. And now that we've narrowed down why our emissions at TLC were higher, we need to find a solution to meet our goals of lower emissions and higher throughput. The fabric cover technology didn't provide the emission reductions needed for our facility during the hot, dry summers, so we decided to look at other options. And based on our discussion with the testing company, we knew that there were other composting facilities achieving low emissions during the hotter seasons. This eventually led us to an alternative technology, which is the extended aerated static pile with a finished compost biofilter. So we'll refer to it as an ESP for the rest of the presentation. It's similar to the fabric cover system where the compost pile is aerated from underneath. And there is a cover on top of the compost for the emission control. The difference here is that instead of a fabric cover, a layer of finished compost is placed on top. This finished compost layer acts as a biofilter, as emissions from the compost rise up through this layer. The microbes degrade the VOCs and ammonia emissions before they can escape the pile. The compost piles can be built side by side, and while it's not shown in this picture, there are sprinklers on top of the pile to provide irrigation, to maintain the moist cover and good environment for the microorganisms. Now, these are some of the potential benefits that really pushed us to explore the ESP option further. Based on compliance test data from other facilities that were using this technology, we saw that they were achieving low VOC and ammonia emissions, and those ESP tests were conducted in the summertime when we were having the most difficulties. The biofilter cover on top is made of our own recycled compost. And another issue with Central Valley, besides the high temperatures, is that the area experiences high winds, which essentially turn the fabric covers into giant sails. And it's an obvious safety issue when the winds get high enough. They actually have to stop operations because they can potentially launch personnel into the air. We don't expect this to be a problem with the ESPs once the biofilter cover has been wetted down. The ESPs require minimal handling of the material, since you would essentially build it and leave it in one place for the entire composting process. The ESPs also can be built in a large monolith pile, which don't require the space in between the piles as windrows do. This allows for more compost to be processed in the same amount of area. Additionally, the ESPs allow us to have more control over the composting process. For example, if a certain area of the ESP is getting too hot, we can make several adjustments, such as increasing the irrigation, adding more cover material, or adjusting the aeration to that section. And lastly, the ESP technology has been utilized in practice and recognized as best available control technology, which is another requirement for being in a non-attainment zone. And with this, the Air District provided us with a permit to operate the ESP technology. However, one of the conditions was that we were required to conduct a compliance test within 9 months after the permit was issued. And this is a tall task, especially for something we never operated before. So I'll pass it back to Carl to explain how our operations team achieved this.
Thank you, Brian. Now I'm going to talk about the actual construction of the EASPs at TLC. TLC is laid out with a series of 12 pads, each with multiple windrows or piles. Each fabric-covered pile is 26 feet wide by 155 feet long, with an 8-foot aisle between each pile. A typical pad is approximately 155 feet long by 230 feet wide and consists of 7 piles with 7 blowers supplying air to underground aeration trenches. The first EASP would be 155 feet long by 140 feet wide, built on the footprint of just 4 piles. We added 3 rows of above-ground perforated PVC piping between these 4 piles. We rerouted the blower output from 3 adjacent piles to these above-ground headers to provide aeration to the aisles in between the piles. Compost mixture was then placed on the footprint shown here over the course of several days. This was the maximum size EASP if we were to use both below and above ground aeration. The resulting EASP has 7 distinct zones. 4 piles plus the 3 aisles in between. A custom-designed PLC monitored temperature and oxygen in 21 locations at 4 depths. The PLC individually controlled aeration using all 7 existing blowers. PLC also controlled a zoned irrigation system to control the biofilter temperature, which ensures low emissions. Each pile and each aisle has its own dedicated zone. Here you can see the irrigation headers with sprinklers spaced approximately every 30 feet. The irrigation control system was later upgraded to a cloud-based system, controlled by mobile phone, to facilitate remote and after-hours control of the irrigation system. This flexibility was important so we could react to biofilter temperatures to maintain compliance. We upgraded the original proprietary wired temperature and oxygen probes to wireless temperature probes, and subsequently eliminated the oxygen probes. The wireless probes communicate directly to the PLC, simplifying data collection and trending. We added variable speed drives to each blower to provide the flexibility to adjust the airflow to achieve PFRP, the process to further reduce pathogens faster and to reduce emissions over the life of the EASP. Since higher airflow translates to higher mass emissions, it is advantageous to turn the blower speed down as soon as possible. Concrete block walls, similar in style to Legos, were added to the sides of the EASPs to mitigate uncontrolled aeration. Ultimately, the PLC was integrated into the TLC Supervisory Control and Data Acquisition System, or SCADA, which further improved our data monitoring capabilities and standardized the collection and trending of operational parameters. The SCADA integration was a huge improvement in our ability to see what was going on, even remotely, and react to it in a timely manner. On the top half of this screenshot, you can see the individual probes of one pile with temperature sensors at multiple depths, the irrigation control valve, and the blower speed control. The lower half of the screenshot shows the status of PFRP and VAR for each monitored point. The SCADA system monitors each point individually, calculating time to compliance, showing red for points not yet in compliance, and green for points that have achieved compliance. Over the next several months, we built 11 more EASPs incorporating these improvements, keeping in mind our looming deadline to prove compliance with the air regulations. At this time, Larry Wong is going to discuss the many phases of research and results and explain how these modifications to the facility will protect our full permitted capacity.
Thank you, Carl. So the research and results presented today are broken up into 3 phases. ESPs 1 through 4 are the early trial and error phase. We had 6 months to get things working before demonstrating that it worked. ESPs 5 and 6 is the official test to prove air quality compliance to regulators. ESPs 7 through 12 is the optimization of the ESP to adopt this technology to our existing facility infrastructure. So we'll be focusing on 2 major compliance requirements for the EASP. First comes from our air permit. We're looking at 2 constituents, ammonia and VOCs. Emission factor targets were calculated for both of these to restore the site back to its full permitted capacity. For ammonia, we want to be below 1.79 pounds per ton of compost mix. For VOCs, we want to be below a target of 0.2 pounds per ton of compost mix. The second compliance requirement comes from the EPA regulations to produce Class A exceptional quality compost. As Carl mentioned earlier, the compost needs to meet certain temperature requirements. For pathogen reduction, PFRP, compost core temperatures need to be above 131 degrees Fahrenheit for 3 days. For vector attraction reduction, compost core temperatures need to be above 104 degrees Fahrenheit for 14 days. Keep in mind, the emission factor is calculated across the entire pile as an average, and the temperature compliance needs to be met at every single monitored point. So the image at the top is our first EASP. As you can see, it's a large block of compost. The white lines on top are the sprinklers, and not seen below in this picture are the air headers providing air to the compost. So the dimensions of this large block of active compost is 150 feet long by 140 feet wide by 7 feet in height. On top of that 7 feet of active compost is a 2-foot biofilter layer. You see on the bottom left image, it's comprised of 2 feet of unscreened finished compost. So pretty much the idea, we have a large mass of active compost that generates emissions during this composting process. And we're relying on a layer of finished compost on top to treat these emissions. So how did we do? Let me direct your attention to the table on the bottom right. Emissions. Ammonia came in at 0.10 pounds per ton mix. That did very well, so this is well below the 1.79 emissions factor target. Biofilter is amazing at treating ammonia, so I give this a green thumbs up. VOCs didn't do quite as well. It came at 1.6 pounds per ton of compost mix, well above our 0.20 emissions factor target, so I give that a red thumbs down. Not meeting the emissions factor target doesn't mean it's a failure, it just means our composting throughput capacity hasn't been restored yet. For operational temperatures, all monitored zones need to pass PFRP for pathogen reduction and VAR to keep vermin and bugs away. 20 out of 21 zones pass. I give this a red thumbs down. Yes, I'm a harsh grader, but it's important to pass at every single monitored point. Otherwise, you must dig out the failed zone and recompost it. So onto our second ESP. We made 4 major improvements. We installed variable speed drives for better air control of the blowers. We implemented push block walls to reduce air intrusion through the sides of the pile. We improved the irrigation coverage of the biofilter cover. And we changed the composition of the biofilter cover. You see on the bottom left, it's a 1-foot layer of unscreened finished compost on the bottom, topped by 1.5 feet of screened finished compost. The screened finished compost has a smaller particle size. This allows for more contact time with emissions passed through and better moisture retention in the cover. So how did we do? Emissions did well for both ammonia and VOCs, coming in at 0.04 and 0.05 pounds per ton of mix, respectively. They're both well below their emissions factor target. Give it a green thumbs up. Operationally, core temperatures all passed for pathogen and vector reduction, but one zone was a little slow to pass. Not quite a green thumbs up, so I give a yellow sideways thumb, because there's still room for improvement. So, on to ESPs 3 and 4. We tried adjusting the air to meet temperature compliance quicker. As Carl brought up earlier, composting is a biological process, with biosolids and wood chip bulking agent. Our hypothesis is that by providing more air early, it speeds up the aerobic microorganisms generating more heat. So the table on the top right, ESP2 had the blowers turned on after the pile was built, and the blowers were on at 50%. ESPs 3 and 4, the blowers were on during the build and were set at 100%. The graph on the bottom right shows ESPs 2 through 4, the compost core temperatures versus time. ESP2 is shown in the blue line, ESP3 is the orange line, ESP4 is the gray line. As you see in the plot, providing more starting air early leads to an increase in early core temperatures. In the table above, providing more air early in the composting process results in 4 days shaved off the average amount of time to meet PFRP. If you look in the final column, the range between the minimum and maximum values for meeting PFRP is significantly reduced, meaning that there's greater reliability of our ESP process. So here's a recap of the first 4 ESPs from our early trial and error phase. ESP1 was only good for ammonia emissions. ESP2 was good for both emissions constituents. ESP3 and 4 were good for both emissions and meeting operational temperature requirements. We've proven in-house that that this works, and now we must officially prove compliance to the air regulators. So in January and February 2019, we had our official compliance test for the regulators. We built 2 smaller 3-row piles, as seen in the top picture. The dimensions of these smaller piles are 150 feet long, 63 feet wide, by 7 feet in height. They're 2.5 feet as the valve filter cover on top. The bottom left picture is of the emissions testing. The bottom right is our results. Emissions, ammonia came in at 0.03, and VOCs came in at 0.12 pounds per ton of compost mix. They're both below our emissions factor targets. These are good, green thumbs up. Operational temperatures all passed for PFRP and VAR, another green thumbs up. So we solved the problem that Brian brought up with our high emissions, and we proved that this technology meets air regulation. But there's still more work to be done to optimize this technology for our facility. So as Carl explained earlier, TLC is designed and constructed for windrow composting. For ESPs 1 through 6, we are rerouting air headers to provide every single row with its own aeration header. The figure on the left shows the existing below ground air headers in green, and the rerouted air headers, above ground air headers in purple. For ESP 7 and 8, we wanted to find out, can this technology work using only the existing below ground air headers? If the above ground air headers are not necessary, a significant capital improvement project can be avoided. So for this test, we're getting rid of the middle air header. And in the diagram in the bottom right, we're testing the hypothesis that there'll be enough lateral air migration through the middle row of compost. So proven in the air regulation compliance test was that the 3-row was of the 3-row ESP configuration, bookended on either side by block walls. ESP 9 is simulating a full-size ESP that's built over several weeks. And we're implementing it with the simplified aeration scheme from ESP 7 and 8 about the above ground air headers. So on week 1, we bookend one side with the block wall. We build 3 rows and bookend the exposed face with biofilter covered material. On week 2, build another 2 rows and bookend the exposed face, biofilter covered material once again. Week 3, we build the final 2 rows, and now you're bookended the block wall. So how do we do? Look at the results from left to right. Operational temperatures for all 3 piles were able to meet PFRP and VAR. This means the below ground air headers were able to provide enough air for the piles to heat up. Give this green thumbs up. Emissions wise, we performed limited emissions testing, and we came back with a surprisingly high result. So how do we end up with higher emissions? We scoured through the test procedures and logs for ESP 7 through 9 and tried to pinpoint what went wrong. We suspected it might have been the biofilter cover. The cover might have been too dry due to power interruptions of the irrigation system. Also, the cover was constructed 6 inches thinner than before. So we built ESP 10. It was a control pile to see if remedies applied to the biofilter cover would restore emissions. We had a thicker cover, we increased irrigation, and we continued with the simplified aeration scheme using only the existing below ground air headers. In the pictures, you can see the cover after an irrigation cycle. Looks like a swamp. So how did we do? Emissions wise, it came at 0.08 pounds of VOC per ton of mix, well below our emission target, and we passed for temperatures as well. So the take-home message is a thick, hydrated biofilter cover is a healthy one. This brings us to our next hurdle for our facility, as it's not designed to manage the quantity of leachate produced by the ESP process. Keep in mind, our previous testing focused on emissions control, not leachate generation. From my previous slide, I mentioned the biofilter cover needs to be wetted to maintain its effectiveness. You see in the figure, to provide this moisture, you have irrigation and precipitation. This must be greater than the evaporation. But if you apply too much irrigation, this results in leachate. You see in the figure, too much irrigation, you get surface runoff, or you can get leachate that passes through the compost. So for our current work, ESP is 1112, we're trying to optimize irrigation to control both emissions and leachate generation. So here's a plot with our preliminary results with our decreased irrigation testing. There's a relationship between ESP irrigation, leachate produced, and emissions. The x-axis is the water applied. The y-axis, on the left blue, the leachate production, and the white on the orange right is the VOC emission factor. So in the plot, we follow the blue line. More leachate is produced, more water applied. While the orange line, we have lower emissions, more water applied. So this is a very helpful tool for finding a balance between emissions and leachate production. So just to recap, ESP performs very well for controlling emissions for the facility. It has efficient use of space, can compost twice as much in the same footprint as before. There's a lower labor requirement with it's a single phase composting process. And we're using a green, environmentally friendly, low cost cover material that's plentiful at our facility. We're very happy with the results of this award-winning technology, and we're moving forward with ESP at TLC. Thank you so much for taking time out of your day to join us for this webinar. Any questions?
Okay, great. Thank you so much, guys. Now we're going to open it up for questions and answers. You can click on attendee chat and you can type in your question right there, and one of the speakers will answer as soon as they can. Okay, there's our first question. You guys want to take that one?
Sure. Just give me a second here. Oops, sorry. Wow. Wood wastes were local agriculture wood waste, usually walnut, peach, whatever was available in the local market.
Okay, you guys can just go down the list of questions and answer at your own pace.
Dennis asks, can you express water use in gallons per day per ton of compost produced? I think Brian could probably answer how many gallons per day we applied. But as far as per ton of compost, I don't know if we looked at that parameter. Brian, you want to speak to the gallons per day?
I don't have that number off the top of my head.
On the order of 10 or 12,000 gallons per day, I think is what we were applying to the ESP. Does that sound about right?
Yeah, that number sounds familiar.
Right.
Initially, we're applying 12,000 a day to get everything wet, and then we reduced it to I think about 5,000 a day. And currently, we're applying about 2,000 gallons a day for reduced irrigation testing.
William Schuberts said low emissions. No, Brian, I don't think we've looked at anything in particular besides VOCs and ammonia. Is that correct?
Yeah, that's correct. The local air district is mainly more focused on those pollutants besides NO2 or N2O for greenhouse gas potential. So we've mainly been focused on just the VOCs and ammonia's emissions so far.
Right. Pedro Modesto asks, the synthetic fabric, what specifications were required? So when the facility was initially designed, we were looking for a material that would, like Brian discussed, would retain moisture and specifically retain a moisture layer on the underside of the cover. So it's a synthetic micropore product while still allowing the cover to breathe. Mark Lang says it sounds as if it was all positive aeration. Yes, this facility was designed for positive aeration. You know, one of the thoughts going with an EASP is, can we make this technology work without a massive capital improvement project? So one of the accomplishments of this series of research was that we're able to use our existing infrastructure with this alternative composting technology and get good results. Are there odor? Angela asks, are there odor problems? We have never had an odor complaint at this facility. Next question, how does this technology compare to anaerobic digestion? What about the business case? I don't.
Well, I mean, the
sure.
biosolids that we're composting comes from the anaerobic digestion from our wastewater treatment plants. I'm not
right. So
sure.
the anaerobic process has already been completed. When we receive the biosolids, they're already Class B biosolids. Our process is to take those Class B biosolids and convert them to Class A EQ compost for beneficial reuse. Edward says, nice job. Can your results be applied to other areas, or is it too specific? Well, you know, the efforts that we went to were specifically to address the problem with a synthetic fabric cover in our climate under our conditions. The synthetic covers are certainly proven under other conditions, so we were really trying to solve the problem at our facility. There's no reason why an EASP with a compost cap as a biofilter would not work in other climates. Mark asks, what is the initial mix TS concentration and final compost TS? I don't have that available, Mark. I'd be happy to find that information for you. Jose asks, do you have problems with plugging of the trench aeration system? Pardon me. Yes, we have had problems with the trench system plugging. But since, you know, when you build an EASP, it sits in place for anywhere from 45 to 65 days. So once every 9 weeks, opening up the trap at the end of the trench and cleaning the trench out is not a laborious task, not a maintenance concern. But yes, the fines from the EASP or from any composting process will find their way into the trench system. Yes. Mark also asks, you mentioned PFRP. Did you test for fecal and show Class A? Yes, we have monthly compliance with fecal coliform. How much wood waste is required per wet ton? Yes, we do buy wood waste. We've bought it on the spot market. We've also just entered into a long-term purchase contract. The wood waste, or the recipe right now is 37% by weight biosolids, 32% fresh wood, and about 31% recycled overs, all by weight. And that fresh wood would have to be moistened when it arrived on site. It arrives on site with single-digit moisture, and we get the moisture up into the 40s or low 50%. Sam says, what's the design power demand for each blower? The blowers are pretty low horsepower. Off the top of my head, 7 kilowatts. Would vibration application usage practical and or economical to keep relatively long-term air fissures from forming, and how would it affect the process? So Ron, that's an interesting question. As constructed, the facility's blowers were designed to be cycled on-off. Constant speed blowers, but cycled on-off in response to oxygen, an oxygen set point. And, you know, the manufacturer pointed out that cycling of the blowers was beneficial because each time the blowers came on, the air took a new path through the compost. The argument was that if you left the blowers on, you would develop a fissure and the air would just continue through that fissure. So with our conversion to variable speed drives, there certainly was that potential that we would develop a path and continue with that path. But I will say that our sampling and our emissions testing shows relative consistency across the entire pile. So there does not appear that there are significant fissures. Mark says, you mentioned a single phase, no curing step. Right. So as the facility was constructed, it was a 3-phase covered windrow process. 3-phase covered active, 3-phase covered mature, and 3 weeks covered active, 3 weeks covered mature, and about 2 weeks curing. With the EASP, it's a single phase. Once you've achieved compost stability, or 62 days, whichever comes first, the compost is cured and you're ready to screen. Steve asks, is the leachate treated on site? So we don't have a leachate treatment system. As Larry talked about, the facility was not really designed for leachate treatment. It's piped to use leachate to re-wet overs, but with a significantly increased amount of leachate, or potentially increased level of leachate from an EASP, we definitely need to look into alternatives for that. So we'd like to optimize the use of irrigation to minimize the production of leachate, but we're also looking into recycling the leachate back onto the top of the compost piles. Mark, I think I already answered that. I think it's 7 kilowatts. How much electricity is used for this? I don't have this answer off the top of my head, William. I can certainly get it to you. Feel free to email me. Can you recycle the runoff? I think I just talked about that. Have I run a life cycle analysis on this process? I'm not sure what perspective you're looking at this from, Philip, but I'd be happy to discuss it further with you if you'd like to email me. I think that's the end of the questions. Any other questions?
Guys, thank you so much. It looks like that is the end of the questions, and if we possibly missed one, feel free to email the speakers, and this recording of the program will be up on our website probably by tomorrow. So thank you so much, guys, and have a great day, have a great weekend. and thanks for joining us.
Thank you so much.
Bye-bye.